In today's lesson, we're going to be learning more about different types of functions and their graphs in function transformations. We're going to begin by creating a library of functions. We're going to complete each table of values for the function and use it to graph the line. Now, although we have been focusing on linear functions primarily throughout this unit, some of the functions that we look at today are nonlinear. Let's get started with y equals x. This is linear. It's one of the most basic linear functions that we have. If you think about this being in slope-intercept form, it's kind of like it has a slope of 1 and a y-intercept of 0. Now, just using those two facts, we could get an idea of what our graph is going to look like, but let's go ahead and fill in the table since that's going to be our primary approach as we look at some of the other function equations. So if y is equal to x, whatever x is, that's what y is. So if x is negative 3, y is negative 3. When x is negative 2, y is negative 2, and so on. So let's go ahead and fill these in. Now all of these now are ordered pairs that we're going to plot on our graph. So we've got negative 3, negative 3, negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2, 3, 3. And sure enough, we can see that it has a slope of 1 and it has a y-intercept of 0. So let's go ahead and draw a point connecting those. Now let's take a look at our next equation. So this one is not linear because it involves an x squared. Anything with an x squared instead is called quadratic. And something special happens here when we have these x values and we start to plug them in. Negative 3, for example, negative 3 squared means negative 3 times negative 3. And we know that a negative times a negative is a positive, so a number squared is always positive. Negative 2 multiplied by itself is positive 4. Negative 1 squared is positive 1. 0 squared is really 0 times 0, which is still 0. 1 squared is 1. 2 squared is 4, 3 squared is 9. So, although we have different x values here, we have a little bit of symmetry in their corresponding y values. So here's what the graph of that looks like. We've got the point negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. And this shape is one that you should have seen before. You may remember that it is called a parabola. All right, next we have the absolute value function. Now we did some work with absolute value equations and inequalities at the beginning of the year. Today we're going to see, well, what would happen if we wanted to graph this, y equals the absolute value of x. And one thing that we talked about earlier in Chapter 1 is that absolute value represents the distance that the number is away from 0 on the number line, and absolute value is always positive. So the absolute value of negative 3 is positive 3, absolute value of negative 2 is positive 2, absolute value of negative 1 is positive 1. The absolute value of 0 is 0, because 0 is 0 spaces away from 0. The absolute value of 1 is 1, got 2, and 3. So these are the ordered pairs for this graph. If we start to plot them, we get negative 3, 3, negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2, 3, 3. And it actually looks like this nice V shape if we connect the points and extend it to the edge of our graph. Always think absolute value is like the V, and there's a V and the word value, so maybe that can help you remember. All right, the last function that we have in our library, another common one that we're going to see today, is called the square root function because it involves the square root of x. Now, you may notice right away that this table looks a little different. First off, there aren't any negative values for x. Well, if we try to take the square root of a negative, it doesn't work. It's not a real number because the square root of something means what number multiplied by itself is equal to that, and you can't have a number multiplied by itself that equals a negative. So we're going to start with 0. The square root of 0 is 0 because 0 squared is 0. The square root of 1 is 1 because 1 squared is 1. Now notice how I skipped a few x values. The next x value I jumped all the way up to 4 because the square root of 4 is 2 because 2 squared is 4. And then I jumped up to 9. The square root of 9 is 3 because 3 squared is 9. I didn't put x equals 2 or x equals 3 because we would have to do the square root of 2 or the square root of 3, which we could get a decimal approximation for those values, but it just doesn't work out to be a nice perfect whole number. So here's what that graph looks like. We've got the point 0, 0, 1, 1, 4, 2, and 9, 3. So it's just going to start here at 0, 0, but then it is going to continue on forever as we move further to the right. So I'm just going to put one arrow on that, just moving to the right. So all of those graphs that we just looked at in our function library are what we would call the original graph or parent graph. Today we're going to see how applying changes to the original equation produces a change in the graph. These changes are called transformations. All right, so we're going to continue by filling in a chart, a summary of transformations. Transformation is just another name for change. These changes will work for any parent equation or parent graph. In each example, C is going to be a number that represents a real number greater than 0. So the first transformation that we're going to look at is called a vertical translation. So I'm actually going to take a moment to switch over here to Desmos. Desmos, you can see it written out here, is a free online graphing tool. And it's a really neat way to explore graphs and see how changes in graphs can occur, which is what we're going to look at today. So I'm going to start by showing you the parent graph of the parabola. Notice the equation over here is y equals x squared. And I want to show you what would happen if we added a number onto the end, like 1. So in the equation, I'm going to write plus 1. And did you see what happened on the graph? It moved up 1 space. If I change that 1 to a 2, it moves up 2 spaces. Change it to a 3, it moves up 3 spaces, and so on. So we see here that adding a number onto the end is going to cause our graph to move up. Now what if we were to subtract a number? So let's go back to the original x squared. Minus 1 is going to make that go down 1 space. Minus 2 goes down 2 spaces. Minus 3 goes down 3 spaces, and so on. So subtracting a number from the end causes our function to go down. Now that was just for the parabola. I wanted to show you that it's going to work the same way with absolute value. Add a number on the end, and it moves up. Subtract a number from the end, and it moves down. And finally, here's our square root function. Works the same way. If I add 4 onto the end, it moves up 4 spaces. If I subtract 3 on the end, it's going to move down 3 spaces. So let's go back to our chart here. We just looked at a vertical translation. So a few examples for our equation. We're going to assume that C represents a positive real number. We could have something like y equals x squared plus C. So just adding a number onto the end is going to cause our graph to move up C number of spaces. And I just chose x squared for the parent graph, but it could have been absolute value of x. It could have been square root of x. So that could be any of them. An example for moving it down, let's do an example with absolute value, would be subtracting a number from the end. That's going to cause it to move down C number of spaces. So it's a vertical translation. Translation is just moving it around on the graph. It's moving in the vertical direction, which is up or down. Now, you may already be thinking what horizontal translation would be based on the name, but let's take a look at what that looks like in Desmos. Okay, so I'm going to start by showing you the parabola again. So here's the original y equals x squared. So to show a horizontal translation, this time I'm going to actually get rid of that squared right there. I'm going to form a parenthesis, and I'm going to start by, let's see, I'm just going to subtract 1 from x inside the parenthesis, and then I'm going to reinsert the squared on the outside of the parenthesis. So if you look at this new graph compared to the original, you should see that it has moved to the right 1 space. Now, in the equation, if I make that x minus 2 in the parentheses, it moves to the right 2 spaces. X minus 3 moves to the right 3 spaces, and so on. So it turns out that when you are subtracting a number inside the parentheses, inside the function, it's going to move to the right. If we want to go the other direction, so let's get back to our original x squared here, we can do that by adding numbers inside the parentheses. So adding 1 on the inside moves 1 space to the left, adding 2 on the inside is 2 spaces to the left, add 3 is 3 spaces to the left, and here's the absolute value graph. So same thing, if you subtract on the inside, it moves to the right. If you add a number on the inside, it's going to move to the left. And the square root function would work exactly the same way. So let's go back to our chart. And we can show here, so if it's a parabola, we have to have parentheses. And the first one that we looked at was subtracting a number on the inside. That's going to move our graph to the right, C number of spaces. And the other situation, so I didn't show you square root on Desmos, but it would work the same way. If it was a square root function, let's say that we wanted to move it to the left, we would add a number on the inside. Inside for square root just means it's inside the square root symbol. So this is going to move left C number of spaces. And it works that same way as well with the absolute value, just like I showed you. So one thing that I think is just a little interesting to comment on here is that the horizontal translation, moving left-right, it appears to be opposite of what we would think. So in the equation, we're subtracting on the inside, but it actually moves to the right. Normally, I think when we think about subtracting, we think about a number line, we think about getting smaller, we might think about moving left, but it's actually opposite. Adding on the inside is what moves it to the left, whereas normally, I think when we think about adding, we might think about it's getting bigger, so it's going to move to the right. So it might be worth just making a little note here that the direction is like the opposite direction as the sign that's actually showing up in the formula. Now, that's not the case for the vertical translation. The vertical translation is the direction that we would expect. Adding, we would expect to get bigger, move up. Subtracting, we would expect to get smaller and move down. It's just the horizontal translation, just the left-right, that appears to be backward, or opposite, I should say. Okay, the next one I want to show you on Desmos, the next one in our chart is called a vertical stretch. So I want to show you this one with the original parabola again. So we just have y equals x squared. We're going to see what happens here when we multiply a number out in front of the x squared. So specifically, I'm going to multiply a 2 out in front to look like this. So I kept the original parabola on there, that's in red. The new parabola that's showing up in blue is the effect when there's a 2 in front. So it looks like it still has the same vertex anchor point of 0, 0 at the bottom, but what you may notice is that it looks like it's a little bit skinnier. It's like a little bit narrower. It looks like it may be kind of stretched out in the vertical direction. If you imagine this parabola made out of like silly putty, if you were to grab the bottom and if you were to grab the top and just stretch it vertically, it's going to make it get a little narrower. And if we change the number in front, it's going to get even more narrow. So let's change it to a 3 in front. It's skinnier. A 4 in front. Whoops, I got rid of my X. A 4 in front is even skinnier. We could do something like a 10 in front. So that is a vertical stretch. So I showed it to you on the parabola, but it's going to work the same way for absolute value. It works the same way for square root. Okay, so the way that this is written out here is using A instead of C. So we're just assuming that A is a real number that's multiplied out in front of our function, and the absolute value of A, if it's greater than 1, that's when it's going to be a vertical stretch. So a few actual examples could be something like y equals 2x squared, or if it's an absolute value, it might be something like 3 times the absolute value of x, or if it's square root, it might be something like 5 times the square root of x. So a description of how the graph changes. If it's one of these two, so if it's the parabola or if it's the absolute value V shape, it's going to look like the graph shape is skinnier or narrower. One of those two words would be a good description of vertical stretch. I want to go back to Desmos for just a minute for the square root function, because when we do a vertical stretch on square root, it's still the idea of grabbing the function and like stretching it out in the vertical direction, but the description of skinnier or narrower doesn't really apply here. I want to show you a few examples of what this looks like. So if we were to put a 2 in front of the square root of x, that green line, see how it looks like it's like vertically stretched out? I would say for this one, it's like the graph gets taller. It has the same anchor point of 0, 0, but it's stretched out taller. Look at how much taller it gets if there's a 3 in front. So I would say let's go back to our chart and maybe just say for this one, it sort of looks like the graph shape is taller. And if you want to even draw a little sketch of that, of what it would look like if it's taller, you can like draw a little picture there off to the side. Okay, we're gonna go back to Desmos, and we're gonna go back to our basic parabola shape. So this time we're gonna see what happens if we have a number in front, but that number in front is some fraction value that's less than 1. So let's see what happens if we make it 1/2. The new graph here is in the green line. See how it looks like it's wider. If we change that fraction to like a 1/3, it's even wider. 1/10 is like really, really wide. So it's kind of the opposite effect if it's a fraction value. And mathematically, the word that we use for this is we call it a vertical shrink, or we say that it's vertically compressed. I kind of like the word compressed here because think about if you were to take like a big metal thing on the top of the graph and a big metal thing at the bottom, and then you start like pushing those metal things closer together. If we were in class, I would like have my hands out to kind of show you a visual of that. But think about it being compressed, so it's going to like squish out and get wider. The same thing will happen with the absolute value graph where it gets a little bit. So let's fill that in our chart here. So vertical shrink or vertical compression is when you have something multiplied in front, but the absolute value of that number is less than 1. So we're talking about like a fraction value that's less than 1 in front. A few examples could be something like y equals 1/3 times x squared, or if it's absolute value, it could be like y equals 1/2 the absolute value of x. Let's make a description here for this, that for either of those, we're going to see that the graph shape is wider. Now I'm going to go back to Desmos again to show you what it looks like if it's the square root. Okay, so there's that original square root graph again. So if we were to put something in front like a 1/2, it's vertically compressed. It's being squished down. It just looks like it's shorter or not as tall. If I change that fraction, it just gets even shorter, even more compressed, even more squished down. So let's go back to our chart, and for the square root, so if you have like a 1/5 in front of the square root of x, it kind of looks like the graph shape is shorter. And again, if you want to draw like a little example of that, it would just be like, let's see if I can make it even shorter. There we go. Yours probably looks better than mine. Just something shorter, looks like it's closer to the x-axis. All right, we have one last kind of transformation called a reflection. So let's go back to Desmos to see what that would look like. All right, so we're going to start again with our parabola. We're going to see a reflection when we introduce a negative sign. So if we put a negative sign in front of the x squared, what happens is that it flips it over. It flips it upside down, or more specifically, we would say that it's reflected over the x-axis. Now, when we change that to the absolute value shape, we're going to see something similar. Put a negative out in front, and it's going to flip it over, making it upside down. And finally, for our square root function, put a negative out in front. Same thing. It's going to reflect it, flip it over the x-axis. All right, so let's make a note of that here in our chart, is that if we have a negative sign out in front of our function, it doesn't matter what the parent function is, I'm just going to put x squared in there, this is going to reflect or flip over the x-axis. And it'll even do that if there's something in front like a -2 in front or a -3 or a -5. That would just mean that not only is it reflected over the x-axis, but it also has like a vertical stretch, for example. All right, the last one I want to show you over here is what happens if we put a negative inside of our function. So we saw that if the negative is outside of our function, if it's in front, it's going to reflect it over the x-axis. If it's inside the function, the best one to see this on is the square root function, because we can see that we're doing the square root of negative x, put a negative sign in there. What happened? This is also a reflection. This time, though, it flips over the y-axis. Now, what's interesting about that y-axis reflection is we actually don't see that with absolute values. So if you look at my equations over here on the left side, watch what happens. If I put a negative in front of the x inside the absolute value, the graph doesn't change, because if you think about it, if this flips over the y-axis, it's going to look exactly the same. So we actually don't see it there. The same is true for our parabola, y equals x squared. If I were to make the x negative on the inside, meaning in the equation the squared is still on the outside, but I have a negative x in parentheses, so it's on the inside, we can see the graph also does not change, because again, if you flip a parabola over the y-axis, it's going to look exactly the same. So I like to show that example just with the square root of x, because that's where we see that it actually looks a little different. So let's put in our chart here that if our negative is inside of our function, we'll use our square root x as an example, it's going to reflect, which is another word for flip, over the y-axis. So that is a summary of our transformations. In the next part of this lesson, in the next video, we're going to apply these transformations and see how we can actually put them to use making new graphs.